PSR B9919 plus 21. You are staring at a strip chart recorder in the radio astronomy lab at Cambridge University. The paper feeds through slowly, line after line of cosmic static, background noise from dying stars. Then something cuts through the chaos. A pulse, sharp, clean. Exactly 1.337 seconds later, another pulse, then another. The pattern never varies. Not by a millisecond. You check the equipment. Everything is functioning normally. The signal continues. Pulse after pulse after pulse. Each one separated by exactly the same interval. This is October 1967. You are graduate student Jocelyn Bell, working under astronomer Anthony Hewish. The signal is coming from coordinates 19 hours, 19 minutes, right ascension, 21 degrees declination. Hence the designation PSR B9919-21. But what you are seeing should not exist in nature. The Lovell telescope at Jodrell Bank Observatory confirmed the signal 3 months later. Radio telescopes across Europe detected the same perfectly timed pulses emanating from the same point in the constellation Vulpecula. The object lies approximately 2,300 light-years from Earth. Each pulse lasts exactly 3/100ths of a second. The interval between pulses remains constant to within 1 part in 10 million. This precision rivals atomic clocks. The signal strength varies slightly, but the timing never deviates. Hewish and Bell published their findings in Nature in February 1968, describing what they termed pulsating radio sources, or pulsars. The signal exhibits characteristics that initially defied explanation. The radio waves arrive at different frequencies with measurable time delays. Lower frequency waves reach Earth microseconds after higher frequency waves from the same pulse. This phenomenon, called dispersion, indicates the signals have traveled through the ionized hydrogen of interstellar space. The amount of dispersion corresponds exactly to the calculated density of free electrons between Earth and the signal's origin point. Each pulse contains energy equivalent to the total power output of our Sun concentrated into 30 milliseconds. The source emits this energy across a narrow beam that sweeps past Earth with each rotation, like a cosmic lighthouse. Here's what makes this impossible. No known stellar process could produce signals with such mechanical precision. Stars are chaotic nuclear furnaces. Their energy output fluctuates constantly due to convection, magnetic field variations, and nuclear fusion irregularities. Even the most stable main sequence stars show measurable brightness variations over timescales of minutes to years. White dwarf stars pulsate, but their periods range from seconds to hours and show significant instability. Variable stars change brightness in patterns that can shift over months or decades. Nothing in the known universe maintains perfect timing over astronomical timescales. The regularity suggested artificial origin. Bell and Hewish initially designated the source LGM-1, standing for Little Green Men. The possibility of extraterrestrial intelligence transmitting beacon signals prompted serious consideration. The signal's narrow bandwidth, precise timing, and lack of Doppler shift variations seem to indicate a deliberately constructed transmission. Radio telescopes searched for similar signals from other star systems. The discovery of 3 additional pulsars with different periods within months ruled out the alien hypothesis. No civilization would construct multiple beacons with arbitrary timing patterns scattered across the galaxy. The standard cosmological model says pulsars are rapidly rotating neutron stars. Neutron stars form when massive stars undergo core collapse during supernova explosions. The stellar core compresses to densities exceeding 100 million tons per cubic centimeter. A neutron star with the mass of our Sun measures only 20 kilometers in diameter. Magnetic field strengths reach 1 trillion times Earth's magnetic field. These fields accelerate charged particles to near light speed, creating narrow beams of radio emission aligned with the magnetic poles. As the neutron star rotates, these beams sweep through space like searchlight beams from a lighthouse. But the neutron star model cannot fully explain PSR B9919 plus 21's extraordinary precision. Neutron stars should gradually slow down as they lose rotational energy through electromagnetic radiation. This spin down should be measurable and irregular due to occasional sudden adjustments called glitches. PSR B99 plus 21 shows the predicted gradual slowdown, but its timing precision exceeds theoretical expectations for rotating neutron stars. The object maintains period stability despite surface irregularities, internal friction, and magnetic field interactions that should introduce timing variations. Some astrophysicists suggest that neutron star interiors behave as superfluids, allowing near frictionless rotation that preserves extraordinary timing precision. Others propose that the magnetic field geometry creates more stable emission patterns than standard models predict. A minority of researchers argue that we observe evidence of exotic physics within neutron star cores, where matter exists in states impossible to recreate on Earth. The extreme conditions might support stable configurations that maintain timing precision through mechanisms we do not yet understand. How does a stellar remnant 20 kilometers across maintain timing accuracy superior to human-built atomic clocks across thousands of years? What forces within neutron star cores preserve such perfect rotational stability? Why do these signals exhibit characteristics that initially seem to require intelligent design? Can conventional physics explain precision this extraordinary emerging from stellar death? Does PSR B 99 plus 21 reveal fundamental properties of matter under extreme conditions that challenge our current understanding? Yet PSR B 1919-21 represents only the beginning of pulsar mysteries, as astronomers would soon discover when they detected a neutron star that occasionally breaks its own rules. The Vela pulsar glitch U are monitoring the radio telescope feeds at Molonglo Observatory when the impossible happens. The pulse arrives 17 microseconds early, then the next one, then every pulse after that. It's February 19th, 1969, and poor B0808-4751, the Vela pulsar, has just violated everything you understand about how dead stars behave. You check the equipment twice. The atomic clocks are perfect. The calibration is flawless. But this neutron star, spinning 656 million kilometers away in the constellation Vela, has somehow accelerated its rotation by 1 part in a million overnight. The Vela pulsar is a neutron star 20 kilometers wide, with the mass of 1.4 suns compressed into a sphere smaller than Manhattan. When it formed 8,000 years ago from a massive stellar collapse, it began spinning 11 times per second, sweeping beams of radio waves across space like a cosmic lighthouse. Radio telescopes at Molonglo Observatory in Australia and Arecibo Observatory in Puerto Rico have tracked its pulses with atomic precision since 1968. These neutron stars are the most accurate natural clocks in the universe, their rotation rates stable to 15 decimal places over decades. Here's what makes this impossible. On February 19th, the Vela pulsar suddenly increased its rotational frequency by 2.01 parts per million. This acceleration released approximately 10 to the 39th joules of energy in a single event. To put this in perspective, the sun produces 10 to the 26 watts continuously. This glitch released more energy than our star generates in 30,000 years, all concentrated into a rotational speed increase that happened faster than any instrument could measure. Dr. Richard Manchester at the Commonwealth Scientific and Industrial Research Organization and Dr. Frank Graham Smith at Jodrell Bank Observatory documented the phenomenon in Nature magazine in 1970. Their measurements showed that before the glitch, the pulsar was slowing down at a rate of 1.24 times 10 to the negative 15th seconds per second, exactly as expected from magnetic braking. After the glitch, it resumed this precise deceleration rate as if nothing had happened, except it was now spinning faster. The standard model of neutron star physics explains this through starquakes. As the neutron star slows due to magnetic braking, its oblate shape becomes unstable. The crust, made of atomic nuclei arranged in a crystalline lattice harder than diamond, suddenly cracks and readjusts to a more spherical configuration. This crustal readjustment decreases the moment of inertia, causing the star to spin faster, just as an ice skater spins faster when pulling in their arms. The energy comes from the elastic strain built up in the crust over thousands of years of gradual deformation. But this explanation cannot account for what happened next. The Vela pulsar has glitched repeatedly. December 24th, 1971, August 1st, 1975, July 12th, 1981, August 19th, 1988. Each time, the rotational frequency increases by similar amounts. Each time, the pulsar returns to its predicted slowdown rate with perfect precision. The timing between glitches shows no pattern. The energy released varies unpredictably. Most disturbing, recent observations by the park's radio telescope show that some glitches are preceded by gradual accelerations over several days, while others happen instantaneously. Some astrophysicists suggest the interior of neutron stars contains superfluid neutrons that can flow without friction. When the crust glitches, this superfluid suddenly couples to the solid crust, transferring angular momentum from the rapidly spinning interior to the slower exterior. But this model predicts recovery times of weeks or months as the superfluid and crust gradually decouple. The Vela pulsar shows recovery signatures lasting years, with exponential healing curves that don't match any superfluid model. Radio observations by the Green Bank telescope and the Lovell telescope at Jodrell Bank reveal another impossibility. Between glitches, the Vela pulsar maintains timing accuracy better than 1 part in 10 to the 14th. This stability rivals the best atomic clocks on Earth. Yet somehow this precision timekeeper can instantly change its rotation rate by amounts that would require restructuring its entire 20-kilometer wide crystalline crust, then immediately resume perfect regularity. How does a neutron star release 30,000 years worth of solar energy without disrupting its atomic level timing precision? What mechanism allows a crystalline structure under pressures exceeding nuclear density to fracture and heal repeatedly without degradation? Why do some glitches show gradual buildup while others appear instantaneous? How can the interior and exterior of a neutron star maintain separate rotation rates for years before suddenly synchronizing? The answers may lie in objects even stranger than glitching pulsars, where the very fabric of spacetime itself begins to break down under forces that make neutron star physics look gentle. SGR 1806-20. You are monitoring gamma-ray detectors across the globe on December 27, 2004. The European Space Agency's International Gamma-Ray Astrophysics Laboratory satellite goes silent first. Then the Solar and Heliospheric Observatory loses telemetry. NASA's Swift Gamma-Ray Burst mission triggers emergency protocols. Radio telescopes from Arecibo to Parkes register interference across every frequency. Something 26,000 light-years away in the constellation Sagittarius has just bombarded Earth with more high-energy radiation than our planet has received from any cosmic source in recorded history. The pulse lasts 0.2 of a second. When the data comes in, the numbers break every scale astronomers use to measure stellar violence. The source is SGR 1806-20, a magnetar spinning once every 7.5 seconds in a star cluster older than complex life on Earth. This is what remains when a star 40 times the mass of our Sun collapses into a neutron star only 20 kilometers across, compressed so tightly that a teaspoon of its material would weigh 6 billion tons. But SGR 1806-20 possesses something that makes ordinary neutron stars seem peaceful. A magnetic field 1 quadrillion times stronger than Earth's, powerful enough to strip the electrons from atoms at a distance of 1,000 kilometers. Dr. Kevin Hurley at the University of California, Berkeley, led the analysis published in Nature in 2005. His team calculated that the gamma-ray burst released more energy in 1/10 of a second than our Sun will produce in its entire 10 billion year lifetime. The initial spike measured 10 to the 39th watts, a brightness that momentarily outshone every other gamma-ray source in our galaxy combined. Radio telescopes detected the expanding shockwave for months afterward, a bubble of ionized gas racing outward at 30,000 kilometers per second. The European Southern Observatory's Very Large Telescope Array tracked the magnetar's location with millisecond precision. SGR 1806-20 sits embedded in a massive star cluster 26,000 light-years from Earth. Yet the December 27th burst temporarily ionized atoms in our upper atmosphere, disrupting radio communications across the Pacific. If this magnetar had been 10 light-years away instead of 26,000, the radiation would have triggered a mass extinction event by stripping away Earth's ozone layer entirely. The standard cosmological model says magnetar giant flares result from starquakes, sudden fractures in the neutron star's crystalline crust that snap magnetic field lines like cosmic rubber bands. The magnetic field energy converts to gamma radiation through a process called magnetic reconnection, similar to, but incomparably more violent than the solar flares that occasionally knock out satellites. The most powerful starquakes should crack the crust by maybe a few centimeters, releasing magnetic energy equivalent to millions of solar flares simultaneously. But here's what makes SGR 1806-20 impossible. The December 27th burst released 10 to the 46 joules of energy, 23 times more than the theoretical maximum a magnetar starquake can produce. Krisa Kuveliotou at NASA's Marshall Flight Center published calculations in Astrophysical Journal Letters, showing that even if the entire magnetic field of SGR 1806-20 converted to gamma radiation at 100% efficiency, it could not account for the observed energy release. The burst exceeded the binding energy that holds the neutron star's magnetic field in place. Some astrophysicists suggest the magnetar underwent magnetic field annihilation, a process where opposing magnetic field lines cancel each other out, converting their entire energy content to radiation. Others propose that SGR 1806-20 briefly formed a hyperfluid core where neutrons flow at friction, allowing magnetic fields to reorganize on timescales faster than nuclear physics permits. A minority of researchers argue that magnetars might tap into zero-point energy fluctuations in the quantum vacuum, accessing energy reservoirs that conventional stellar physics cannot measure. The Rossi X-ray Timing Explorer detected periodic pulsations embedded in the afterglow, oscillations at frequencies that correspond to the magnetar's rotation and its theoretical crustal vibration modes. But these oscillations displayed phase coherence lasting far longer than any known physical process can maintain. It's as if the neutron star rang like a bell for hours, when the intense magnetic fields should have damped any vibrations within milliseconds. Radio observations from the Green Bank telescope revealed that SGR 1806-20 continues emitting coherent radio pulses with timing precision superior to automaton's, despite the violent restructuring its magnetic field endured during the giant flare. The magnetar's rotation period has remained stable to within nanoseconds over the past 2 decades, suggesting an internal structure more rigid than any material known to physics. How does a dead star access energy reservoirs that exceed its own magnetic field capacity? What mechanisms maintain structural coherence during an explosion that should tear apart the very forces holding the neutron star together? Why do these cosmic lighthouses continue keeping perfect time even after unleashing the energy equivalent of stellar formation? Can matter compressed beyond nuclear density tap into energy sources that our understanding of thermodynamics cannot account for? How many more magnetars in our galaxy possess this same impossible potential? The radio telescopes now turn toward another impossible timer, one that spins 643 times per second without missing a beat. PSRJ Wevinson 482446A. You are watching the Green Bank telescope's data stream at 2 in the morning when the pulse arrives, 716 times in a single second. The signal is so fast your equipment can barely register each individual beat before the next one hits. The neutron star designated PSRJ 1482446AD is spinning faster than a kitchen blender, faster than a jet engine, faster than anything in your experience of how matter behaves. Each pulse marks one complete rotation of a city-sized object with the mass of our sun. The surface of this dead star is moving at 71,000 kilometers per second, 24% the speed of light. This shouldn't be possible. The discovery came through the Parkes Radio Telescope in Australia in 2005. Scott Ransom of the National Radio Astronomy Observatory and his team were conducting a survey of globular cluster Terzan 5 when they detected the signal. The pulsar sits 28,000 light-years away in the constellation Sagittarius, embedded in one of the densest stellar regions of our galaxy. Initial measurements showed a rotation period of 1.396 milliseconds. Follow-up observations with the Arecibo Observatory confirmed what the data suggested. This neutron star rotates faster than any other known object in the universe. The physics are staggering. PSR J1148 2D446 AD, has compressed roughly 1.4 times the mass of our Sun into a sphere just 20 kilometers across. The density exceeds 100 million tons per cubic centimeter. A sugar cube of this material would weigh 6 billion tons on Earth. The magnetic field strength reaches 1 trillion times that of Earth's magnetosphere. Yet despite these extreme conditions, the pulsar maintains timing precision that rivals the best atomic clocks humans have ever constructed. The pulse arrival times vary by less than 1 microsecond over months of observation. The standard cosmological model says millisecond pulsars form through a process called recycling. An old neutron star in a binary system accretes matter from its companion, gradually spinning faster as angular momentum transfers from the infalling material. The process can take millions of years, slowly accelerating the dead star until it reaches rotation rates measured in milliseconds. The theory explains how these cosmic lighthouses achieve such incredible speeds while maintaining their structural integrity through the conservation of angular momentum and the neutron star's crystalline crust. But the model struggles with PSR J1148 2446 AD's extreme parameters. At 716 rotations per second, this neutron star approaches the theoretical breakup velocity, where centrifugal force should overcome gravitational binding. Standard calculations suggest that neutron stars spinning faster than 700 times per second should tear themselves apart, flinging their outer layers into space. The surface gravity at the equator drops to nearly zero. The centrifugal acceleration reaches 2.5 times 10 to the 12th meters per second squared. No known equation of state for neutron star matter can fully account for how this object maintains its coherence while spinning at such velocities. Some astrophysicists suggest that exotic matter states might stabilize ultrafast pulsars. Theoretical work by Dr. Fariel Azoliel at the University of Arizona and colleagues proposes that neutron stars could contain strange quarks or other non-standard particles that strengthen the stellar structure beyond current models. Alternative theories invoke crystalline crusts with tensile strengths approaching nuclear binding forces, or magnetic field configurations that provide additional structural support against centrifugal disruption. A minority of researchers propose that these objects might not be neutron stars at all, but rather strange quark stars with fundamentally different internal physics. The timing precision presents its own mystery. Atomic clocks achieve their accuracy through the regular oscillations of cesium atoms at 9.19 GHz. PSR J1748 2446 AD pulses at 716 Hz, while maintaining comparable stability over astronomical timescales. The lighthouse mechanism that produces these radio beams involves charged particles streaming along magnetic field lines, accelerating to relativistic speeds, and emitting radiation in narrow cones. The entire system operates with clockwork precision despite the violent physics occurring at the neutron star surface. Recent observations with the Green Bank telescope have detected subtle variations in the pulse profile, suggesting that the neutron star's magnetic field structure evolves over time. The emission mechanism appears more complex than simple dipole radiation models predict. Paulo Freire of the Max Planck Institute for Radio Astronomy has documented correlations between pulse intensity and arrival time that hint at magnetospheric dynamics beyond current theoretical frameworks. How does a dead star spinning at nearly 1/4 the speed of light maintain atomic clock precision? What exotic physics allows neutron matter to remain coherent under such extreme centrifugal stress? Why do the radio beams carry information about magnetic field structures that seem to violate standard pulsar models? Can any equation of state for ultradense matter explain these observations? What does this precision tell us about the fundamental nature of time itself in extreme gravitational environments? But PSR J1748 2446E represents just one member of a binary system that challenges everything we thought we knew about how dead stars interact across the cosmic void. PSR J0737 3039, you are monitoring the Parkes Radio Telescope in New South Wales when the data stream from pulsar J0737 -3039 suddenly doubles. Two distinct pulse signatures, two different periods. Two neutron stars locked in an orbital dance so tight they complete a revolution every 2 hours and 24 minutes. The computer screen shows something that shouldn't be possible: a binary pulsar system where both stars are active pulsars, beaming radio waves across the galaxy like cosmic lighthouses spinning in perfect synchronization. The discovery came in 2003 when astronomer Michael Kramer and his team at the Max Planck Institute for Radio Astronomy identified what appeared to be a standard millisecond pulsar. But continued observations revealed the impossible: a second pulsar signal embedded in the data. Pulsar A spins once every 22.7 milliseconds, while Pulsar B rotates every 2.8 seconds. They orbit their common center of mass at a distance of just 1.2 million kilometers, 3 times the distance between Earth and the Moon. Here's what makes this system extraordinary. The orbital period is decreasing by exactly 7 microseconds per day. The two neutron stars are spiraling toward each other as their orbit decays. Einstein's theory of general relativity predicts this should happen as the system loses energy by radiating gravitational waves, ripples in spacetime itself that carry momentum away from the orbiting masses. The rate of orbital decay matches Einstein's predictions to better than 0.05% accuracy. This represents the most precise test of general relativity ever conducted in the strong field regime. Each neutron star contains 1.3 solar masses compressed into a sphere just 20 kilometers across. Surface gravity reaches 100 billion times Earth's gravity. The orbital velocity approaches 1,000 kilometers per second, nearly 1% of the speed of light. Under these extreme conditions, space-time warps so severely that classical physics completely breaks down. The Arecibo Observatory confirmed these measurements through 5 years of continuous monitoring. The Very Large Array New Mexico provided additional timing data. The European Pulsar Timing Array Consortium tracked the system's evolution across multiple radio telescopes. Every observation confirmed the same impossible precision. Gravitational waves are carrying away orbital energy at exactly the rate Einstein calculated in 1915. The standard cosmological model says gravitational waves represent oscillations in the fabric of spacetime itself. When massive objects accelerate, they create ripples that propagate outward at the speed of light. These waves are incredibly weak. Passing gravitational waves stretch and compress space by less than 1 part in 10 to the 21st power. For a binary neutron star system, the wave amplitude depends on the masses, orbital separation, and inclination angle according to precise mathematical relationships derived from general relativity. But the double pulsar system reveals something mainstream physics cannot fully explain. The timing precision required to measure orbital decay at the microsecond level demands that both pulsars maintain absolutely stable rotation rates over decades. Neutron star magnetospheres should introduce timing noise through magnetic field variations, stellar wind interactions, and magnetospheric plasma instabilities. The observed stability exceeds theoretical predictions by several orders of magnitude. Some astrophysicists suggest that the binary configuration itself creates a unique magnetic environment that suppresses the usual sources of timing noise. The gravitational field of each neutron star may stabilize the other's magnetosphere through tidal effects. Alternative theories propose that quantum vacuum fluctuations in the intense gravitational field create feedback mechanisms that naturally stabilize pulsar rotation rates. The orbital geometry adds another layer of mystery. Pulsar A's beam sweeps across Earth once per orbit, creating eclipse conditions that last 24 seconds. During these eclipses, Pulsar B's signal shows systematic variations that suggest the plasma environment between the stars exhibits structure not predicted by standard magnetohydrodynamic models. The eclipse mapping reveals density gradients and magnetic field configurations that require physics beyond current neutron star atmosphere theories. Radio observations show that both pulsars exhibit precession effects consistent with frame dragging, the rotation of spacetime itself caused by the spinning neutron stars. The measured precession rates match general relativistic predictions, but they also reveal that the neutron star equations of state must be stiffer than previously thought. The stars cannot be composed entirely of ordinary nuclear matter. exotic particles or phase transitions in the dense core may be required to explain the observed moment of inertia values. Why do both neutron stars remain active as radio pulsars when binary evolution models predict one should have been spun down during the accretion phase? How does the system maintain timing stability that exceeds the theoretical limits imposed by magnetospheric physics? What exotic matter states exist in neutron star cores dense enough to support the observed moment of inertia? Why does the eclipse plasma show structure that violates standard neutron star wind models? How many other binary pulsar systems remain hidden in the galaxy, waiting to test the limits of general relativity? As gravitational wave detectors like the Laser Interferometer Gravitational Wave Observatory finally achieved direct detection decades later, they would find that the cosmos holds even stranger objects, dead stars that somehow nurture planets in orbits where no worlds should exist. PSR B1257+12. You're monitoring the Arecibo Radio Telescope's data stream on a routine night in 1990. The massive dish sits silent in the Puerto Rican jungle, but its electronic ears are locked onto a dead star 1,200 light-years away. The pulsar PSR B12557+12 has been sending its lighthouse beam of radiation toward Earth for millions of years. A neutron star spinning 38 times per second, its magnetic field so intense it would rip the iron from your blood at a distance of 1,000 kilometers. Then you notice something in the timing data that makes you check your calculations 3 times. The pulses are arriving early, then late, then early again, in a pattern that repeats every 66 days, then 98 days, then over 3 years. The dead star is wobbling. Astronomer Alexander Wolfs-John of Pennsylvania State University published his findings in the journal Nature in 1992. The timing variations in PSR B1257+12's radio pulses revealed the gravitational influence of 3 planetary companions orbiting the neutron star. The innermost planet completes an orbit every 25 days at a distance of 36 million kilometers. The second planet orbits every 66 days at 53 million kilometers. The third takes 98 days at 67 million kilometers. The 2 outer worlds possess masses 4 times that of Earth. Super-Earths is locked in gravitational resonance around a stellar corpse. Here's what makes this impossible. Neutron stars form when massive stars explode as supernovae, releasing more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. The explosion vaporizes everything within light years. Temperatures reach 100 billion Kelvin, 6,000 times hotter than the sun's core. The neutron star itself maintains surface temperatures of 1 million Kelvin, while generating magnetic fields 1 trillion times stronger than Earth's. The radiation environment around PSR B157+12 bathes any orbiting object in high-energy particles equivalent to standing next to a nuclear reactor core. This is not a place where planets should exist. The standard cosmological model says planetary formation occurs in protoplanetary disks around young stars, where dust and gas gradually accrete over millions of years in relatively stable, cool environments. Planets require precise temperature ranges for solid material to condense and stick together. The supernova that created PSR B1257+12 would have obliterated any pre-existing planetary system, ejecting debris at thousands of kilometers per second into interstellar space. The neutron star's formation marks the end of planetary possibilities, not the beginning. But the data doesn't support this timeline. The 3 planets orbit in almost perfectly circular paths, suggesting they formed in place rather than being captured from elsewhere. Their orbital resonances, the outer 2 planets, complete exactly 3 orbits for every 2 of the inner planet, indicate a stable system that has persisted for millions of years. Spectroscopic analysis shows no evidence of the heavy elements that would result from supernova debris accretion. Some astrophysicists suggest the planets condensed from a disk of material that somehow survived the supernova explosion, or formed from fallback material that reaccumulated after the blast. Others propose the planets migrated inward from distant orbits, where they originally formed before the star's death. The radiation measurements tell a different story. The National Aeronautics and Space Administration's Hubble Space Telescope and ground-based observatories have monitored PSR B1257+12 for 3 decades. The neutron star emits X-rays, gamma rays, and charged particles at levels that should strip atmospheres and sterilize any rocky surface within astronomical units. The magnetic field lines channel particle streams that would cook these worlds from the inside out. Yet the planets maintain their orbits with clockwork precision, their masses unchanged by the stellar furnace they call home. The European Southern Observatory's Very Large Telescope has detected no thermal emissions from the planet's surfaces, suggesting temperatures consistent with objects in permanent shadow. This contradicts models predicting that neutron star radiation should heat the planets to thousands of degrees. The worlds appear to exist in a state of thermal equilibrium that no current model can explain. They orbit a star that died in violence, in an environment that should destroy them, showing orbital stability that suggests they have been there since before their sun exploded. Radio observations reveal additional complexity. The pulsar's magnetic field interacts with the planetary magnetospheres, if they exist, in ways that create subtle variations in the radio emission timing. These interactions suggest the planets possess their own magnetic fields strong enough to deflect some of the neutron star's particle wind. Only planets with active cores or exotic compositions could maintain such fields in this radiation environment. How do rocky planets survive temperatures that melt iron and radiation that strips electrons from atoms? What mechanisms allows planetary formation in the aftermath of stellar death? Are these worlds made of materials that don't exist in our solar system? Could exotic matter states persist in the extreme physics environment around neutron stars? Why do the orbital resonances suggest these planets have been dancing around their dead star for geological timescales? The signal from PSR B1257 plus 12 continues to arrive every 26 milliseconds, each pulse carrying information about 3 impossible worlds that shouldn't exist, yet persist in their lethal dance around a stellar graveyard where the laws of planetary science break down completely. RX J0806.3 plus 527. You are monitoring the Chandra X-ray Observatory's data feed when the pattern emerges. Every 321 seconds. Precise. Mechanical. Like a cosmic metronome beating in the constellation Cancer. 800 light years from Earth. The X-ray flux spikes dim spikes again. Your instruments are detecting something that resembles a stellar heartbeat, but the rhythm is impossibly fast for what you're observing. The source is RxJ0806.3 plus 1527, discovered in 1996 by the Rosat X-ray satellite during its all-sky survey. Follow-up observations by the European Space Agency's XMM Newton telescope confirmed what seemed impossible. 2 white dwarf stars locked in an orbital dance so tight they complete a full revolution in just 5 minutes and 21 seconds. The Hubble Space Telescope's spectroscopic analysis revealed orbital velocities exceeding 1,000 kilometers per second. These stellar remnants, each roughly the mass of our Sun, compressed into objects the size of Earth, are separated by less than 80,000 kilometers. Closer than many communication satellites orbit our planet. Here's what makes this system impossible to reconcile with current models. According to Albert Einstein's general theory of relativity, objects this massive moving this fast should generate gravitational waves powerful enough to drain orbital energy at an extraordinary rate. The mathematics are unforgiving. Gravitational wave calculations, confirmed by the Laser Interferometer, Gravitational Wave Observatory's detection of similar mergers indicate that white dwarf binaries at this separation should spiral inward and merge within 10 million years. Yet RX J0806.3 plus 1527 shows no evidence of orbital decay. If anything, some measurements suggest the orbital period might be increasing. The X-ray emissions themselves defy explanation. Each pulse represents roughly 10 to the 31st watts of energy, equivalent to the total power output of 10 billion suns. The X-rays originate from a accretion stream, where material torn from one white dwarf impacts the surface of its companion at speeds approaching 2,000 kilometers per second. The impact zones reach temperatures exceeding 100 million Kelvin, hot enough to fuse helium into carbon in microseconds. Yet the energy distribution across the X-ray spectrum doesn't match theoretical models for white dwarf accretion. The standard cosmological model says that close binary systems like this represent the final stages of stellar evolution. Two sun-like stars, having exhausted their nuclear fuel, shed their outer layers and leave behind dense white dwarf cores. Gravitational wave radiation gradually shrinks their orbit until they either merge in a Type Ia supernova explosion, or, in rare cases, form an extremely close binary that emits X-rays as material transfers between the stars. The system should be unstable on astronomical timescales, spiraling toward inevitable collision. But the observational data reveals inconsistencies that challenge this narrative. The European Southern Observatory's Very Large Telescope has monitored RX J0806.3 plus 1527 for over 2 decades, searching for signs of orbital evolution. The precision timing required to detect orbital decay in such systems pushes observational technology to its limits. Each 321-second pulse must be measured with microsecond accuracy across years of observation. Instead of the predicted shortening orbital period, some measurements suggest the opposite trend. The X-ray spectrum presents another puzzle. The National Aeronautics and Space Administration's Nuclear Spectroscopic Telescope Array has revealed emission lines that shouldn't exist in white dwarf atmospheres. Iron nuclei stripped of all but 2 or 3 electrons indicate magnetic field strengths exceeding 100 million Gauss. Fields so intense they would compress atoms into needle-like shapes and alter the fundamental constants of quantum mechanics. The magnetic field geometry appears to remain stable despite the extreme orbital dynamics, suggesting an unknown mechanism maintains the field configuration. Some astrophysicists suggest that RX J0806.3 plus 1527 represents a fundamentally different type of object than previously understood. The system might contain white dwarf stars with exotic matter cores, remnants of primordial black holes formed in the early universe, or evidence of modified gravity at extreme scales. Alternative theories propose that the gravitational wave calculations themselves might be incomplete, missing some aspect of space-time dynamics in the strong field regime where general relativity approaches its limits. The timing precision of the X-ray pulses raises additional questions about the system's internal structure. Atomic clocks aboard GPS satellites, accurate to nanoseconds, pale in comparison to the regularity of RX J0806.3 1527's emissions. The mechanism that maintains this precision while material streams between the stars at relativistic velocities remains unexplained. Computer simulations of the accretion process struggle to reproduce both the observed pulse profile and the remarkable timing stability. Recent observations by the James Webb Space Telescope's infrared instruments have detected unexpected thermal emissions from the system. The infrared signature suggests temperatures and energy distributions that don't align with white dwarf models. The data indicates that RX J0806.3 plus 1527 might be radiating energy through channels beyond the known electromagnetic spectrum, possibly including gravitational wave modes not predicted by standard theory. What mechanism prevents this system from following the gravitational wave in spiral that theory demands? How does it maintain X-ray pulse precision while matter streams at relativistic speeds between the stars? Why do the magnetic field configurations remain stable in such an extreme environment? Could this system represent physics beyond general relativity, operating at the intersection of extreme gravity and quantum mechanics? What unknown force balances the energy loss that should drive these stars toward merger? Yet even as RX J0806.3 plus 1527 challenges our understanding of stellar evolution and gravitational physics, it hints at complexities in cosmic timekeeping that extend far beyond white dwarf binaries, reaching into the precise clockwork of spinning neutron stars, where millisecond timing meets the deepest mysteries of space and time. PSR J1903 plus 0327, you're monitoring the Arecibo Observatory's pulsar survey data stream when a timing pattern stops you cold. March 2006. The radio telescope has been mapping millisecond pulsars across the galactic plane for months, cataloging their predictable clockwork signals. But this one is different. PSR J1903 is spinning at 465 rotations per second, fast enough to qualify as a millisecond pulsar. Yet its radio pulse arrives early, then late, then early again in a pattern that traces a 95-day orbital cycle around a companion star. The Doppler shift signature is unmistakable. This dead star is dancing. The Arecibo Observatory first detected PSR J903 plus 0327 during the Pulsar Arecibo L-band feed array survey, a systematic search for new pulsars conducted by astronomer Duncan Lorimer and his team at West Virginia University. The object sits 7,000 light-years away in the constellation Aquila, spinning with a period of 2.15 milliseconds. A neutron star rotating so fast that its equatorial surface moves at roughly 20% the speed of light. Initial observations published in Science in 2008 revealed something extraordinary. This millisecond pulsar occupies a highly eccentric orbit with an eccentricity of 0.44, taking it from 1.3 to 7.8 times the distance from Earth to the Sun during each orbital cycle. Here's what makes this configuration impossible. Millisecond pulsars form through a process called recycling, where a neutron star accretes matter from a companion star over millions of years. The infalling material spins up the dead star like a cosmic gyroscope until it achieves rotation periods measured in milliseconds. This recycling process requires the neutron star to orbit very close to its companion, close enough for mass transfer to occur, and the gravitational interactions during this phase should circularize the orbit. Every known millisecond pulsar binary system follows this pattern. Tight circular orbits with low eccentricity values, typically below 0.01. Subsequent observations using the Green Bank telescope and the Lovell telescope at Dodrell Bank Observatory revealed the companion star's properties through optical spectroscopy. The companion is a main sequence star, roughly 20% more massive than the Sun, burning hydrogen in its core with a surface temperature of 6,000 Kelvin. This places it firmly in the category of normal stellar evolution. Not a white dwarf, not a neutron star, but an ordinary star that should have no business sharing such an eccentric orbit with a recycled pulsar. The timing measurements published by astronomer Scott Ransom at the National Radio Astronomy Observatory demonstrated orbital precision down to microseconds, confirming an eccentricity that violates every model of binary millisecond pulsar formation. The standard cosmological model says millisecond pulsars require stable, long-term mass transfer to achieve their rapid rotation rates. The neutron star must remain in a close circular orbit with its companion for tens of millions of years, while material flows steadily from the normal star onto the dead star's surface. High eccentricity orbits prevent this process, because the neutron star spends most of its time too far from the companion for mass transfer to occur, and the brief close approaches would create violent, unstable interactions rather than steady accretion. The recycling mechanism simply cannot operate in an orbit like PSR J1903 plus 0327's current configuration, but the pulsar's spin rate proves recycling occurred. Some astrophysicists suggest this system began as a hierarchical triple star configuration, 2 stars in a tight binary orbit, with a third star orbiting at a greater distance. In this scenario, the neutron star formed through supernova explosion within the inner binary underwent recycling while orbiting its close companion, then experienced a gravitational encounter with the third star that ejected the original companion and captured the outer star into the current eccentric orbit. Computer simulations by researchers at Northwestern University demonstrate that such interactions can produce the observed orbital parameters, but they require extraordinarily precise timing in stellar masses that occur in less than 1% of triple star systems. Alternative theories propose that PSR J1903 plus 0327 formed through exchange interactions in a globular cluster environment, where dense stellar populations enable complex gravitational encounters between binary and single stars. Yet the system's location in the galactic disk, rather than a cluster environment, challenges this explanation. Radio astronomer Ingrid Stairs at the University of British Columbia has noted that the system's kinematics show no evidence of cluster escape velocity, suggesting formation in the field population rather than a dense stellar environment. Why does this dead star maintain an orbit that should have prevented its formation? How did recycling occur in a system that couldn't support mass transfer? What happened to the original companion that enabled the neutron star's rapid rotation? Could hierarchical triple systems survive supernova explosions more often than stellar evolution models predict? Why do we find this impossible configuration in a region of space where such complex interactions should be extremely rare? Sometimes the universe preserves evidence of violent encounters that should have destroyed everything involved, leaving behind signatures of cosmic catastrophes written in orbital mathematics. Jaminga. You are monitoring the gamma-ray sky through the Fermi Large Area Telescope when a pulse arrives from 650 light-years away. 237 milliseconds later, another pulse, then another. The pattern is metronomic, precise, unbreaking. Your screens show gamma rays so energetic they could pass through 1 trillion miles of lead without slowing down. The source is a dead star barely 20 kilometers across, spinning 4 times every second, painting the cosmos with radiation that makes nuclear reactors look like birthday candles. You switch to radio frequencies, expecting the characteristic lighthouse beam that defines every pulsar in the known universe. The radio telescope shows nothing, static, silence. The gamma-ray storm continues, but in radio wavelengths, this object might as well not exist. The Jaminga pulsar was first detected by the second small astronomy satellite in 1972 as an unidentified gamma-ray source. For nearly 2 decades, astronomers called it a Jaminga, Milanese dialect, meaning it's not there, because no optical or radio counterpart could be found. In 1991, the Roentgen satellite finally revealed X-ray pulsations, with a period of 237 milliseconds. The Hubble Space Telescope confirmed the optical counterpart in 1993, but radio telescopes from Arecibo to the Green Bank Observatory detected virtually nothing where the most powerful radio pulsar should exist. Here's what makes this impossible according to standard pulsar physics. The Lighthouse model explains pulsar emission through magnetic field acceleration of charged particles near the neutron star's magnetic poles. As the star rotates, these emission beams sweep across space like cosmic lighthouses. The process should generate radiation across the entire electromagnetic spectrum. Radio waves, X-rays, and gamma rays all produced by the same underlying mechanism. The magnetic field strength should be roughly 10 to the 12th Gauss, 1 trillion times stronger than Earth's field. The rotation should power emission from radio frequencies through gamma rays with predictable intensity ratios. The Fermi Gamma Ray Space Telescope has monitored Jaminga continuously since 2008. The data shows gamma ray pulses with luminosity exceeding 10 to the 34 ergs per second, more energy per second than the sun produces across all wavelengths. The pulse profile displays 2 distinct peaks separated by roughly half the rotation period, exactly matching the lighthouse geometry. The spectrum extends from 100 million electron volts to over 10 billion electron volts. Radio observations with the most sensitive telescopes on Earth detect flux densities below 1 millijansky, effectively zero signal. The standard cosmological model says Jaminga represents a normal rotation-powered pulsar, where magnetic field acceleration creates particle cascades that emit synchronized radiation across all frequencies. The magnetic field threading the neutron star's crust should funnel charged particles into narrow beams emanating from the magnetic poles. These beams should contain radio waves at the low energy end and gamma rays at the high energy end, all generated by the same synchrotron and curvature radiation processes. The radio emission should be detectable at distances up to several thousand light years, given the gamma ray luminosity. But Jaminga produces gamma rays without radio counterparts. The radio to gamma ray ratio is at least 10,000 times lower than standard pulsar models predict. Some astrophysicists suggest Jaminga represents a new class of gamma ray only pulsars, where the radio emission beam misses Earth while the gamma ray beam strikes our detectors. Others propose that the magnetosphere structure differs fundamentally from conventional pulsars, creating emission regions that produce gamma rays through different physical processes. Alternative models invoke pairs-R-starved gaps where insufficient electron-positron pairs form near the magnetic poles, suppressing radio emission while maintaining gamma ray production through inverse Compton scattering. The Fermi telescope has identified over 20 similar objects, neutron stars that pulse in gamma rays but remain radio quiet or radio faint. The population suggests the Jaminga-type pulsars might outnumber conventional radio pulsars by factors of 5 to 10. If true, our census of galactic neutron stars could be incomplete by orders of magnitude. The local bubble, the cavity in the interstellar medium surrounding our solar system, shows gamma-ray emission that could originate from additional undetected Geminga-class objects. Recent studies using the high-energy stereoscopic system telescopes have detected extended gamma-ray emission around Geminga, suggesting that high-energy electrons and positrons are escaping the magnetosphere and interacting with interstellar magnetic fields. This pulsar wind nebula extends several degrees across the sky, indicating that Geminga has been injecting relativistic particles into local space for hundreds of thousands of years. The energy requirements exceed what conventional radio pulsar models allow for objects of Geminga's age and rotation period. What mechanism creates gamma-ray emission without corresponding radio signals? How can magnetic field acceleration operate selectively across the electromagnetic spectrum? Why does the standard lighthouse model fail for objects that otherwise behave exactly like normal pulsars? Are we observing geometric accidents or fundamental differences in neutron star physics? How many dead stars populate our galaxy if gamma-ray only pulsars outnumber radio-detectable objects by an order of magnitude? The silence in radio wavelengths points toward neutron star populations that remain completely hidden from traditional pulsar surveys. PSR J8847-2330. You are monitoring the radio telescope arrays at the Parkes Observatory in New South Wales, tracking the clockwork precision of dead stars across the galaxy. The date is March 14, 2008. Your screens display the rhythmic pulses of PSR J8847-2330, a neutron star 18,000 light-years away in the constellation Scutum, broadcasting its radio beacon every 1.39 seconds with the reliability of an atomic clock. You've been tracking this stellar corpse for 3 years. Its timing residuals measure less than 10 microseconds, more precise than any timepiece humanity has ever built. Then, at 14 hours, 23 minutes, and 47 seconds universal time, the signal stops, not weakens, not drifts, stops. The universe's most reliable metronome has gone silent. The Parkes 64-meter radio telescope, operated by the Commonwealth Scientific and Industrial Research Organization, has been conducting systematic pulsar timing observations since 1968. PSR J8847-2330 was discovered during the Parkes Multibeam Pulsar Survey, cataloged by researchers led by astrophysicist Duncan Lorimer at the University of West Virginia. The pulsar exhibits the standard characteristics of its class. A neutron star with a mass approximately 1.4 times that of our Sun, compressed into a sphere 20 kilometers in diameter, spinning once every 1.39 seconds, and sweeping its radio beam across Earth with each rotation. The object radiates at frequencies centered around 1400 megahertz, with a pulse width of approximately 23 milliseconds. Its period derivative indicates a magnetic field strength of roughly 4 times 10 to the 13th power Gauss, 1 trillion times stronger than Earth's magnetic field. The timing precision before March 2008 allowed astronomers to predict the arrival of each pulse to within microseconds, making it one of the most stable periodic phenomena in the known universe. Here's what makes this impossible. On March 14, 2008, PSR J8847-2330 entered what researchers term a null state, complete radio silence that lasted 63 days. During this period, no detectable radio emission emerged from the neutron star's location despite continuous monitoring by multiple radio telescopes worldwide. Then, on May 16, 2008, the pulses resumed with identical timing characteristics, as if the intervening silence had never occurred. The timing residuals showed no drift, no accumulated error, no indication that the neutron star's rotation had been affected. Since its discovery, PSR J8847-2330 has exhibited 17 documented null episodes, ranging from 18 days to 112 days in duration. Follow-up observations published in the Astrophysical Journal by researchers at Jodrell Bank Observatory confirm that during null states, the pulsar remains completely radio quiet across all observed frequencies. Most remarkably, when transmission resumes, the pulse timing picks up exactly where it would have been if the neutron star had continued pulsing throughout the silent period. The standard cosmological model says that pulsar radio emission originates from charged particles accelerated along magnetic field lines in the neutron star's magnetosphere. These particles create coherent radio waves as they spiral around magnetic field lines extending thousands of kilometers above the stellar surface. The lighthouse effect occurs as the neutron star's magnetic axis rotates with respect to its spin axis, sweeping the radio beam across space. This mechanism should be as constant as the star's rotation itself, powered by the rotational kinetic energy of a trillion ton spinning magnet. But the null states of PSRJ 88472330 suggest something far more complex. The neutron star's rotation continues unchanged during silent periods, as confirmed by X-ray observations from the Chandra X-ray Observatory showing consistent thermal emission from the stellar surface. The magnetic field strength, inferred from spin-down rates, remains constant. Yet somehow, the entire radio emission mechanism, the acceleration of charged particles, the generation of coherent radio waves, the lighthouse beam itself, completely shuts down and later restarts with perfect precision. Some astrophysicists suggest that PSRJ 8847-2330 represents a new class of intermittent pulsars, where the magnetosphere undergoes complete state changes. Ingrid Stairs at the University of British Columbia has proposed that variations in the neutron star's magnetic field configuration could temporarily eliminate the radio emission zones. Alternative theories invoke changes in the plasma density surrounding the neutron star or sudden reorganizations of the magnetospheric current systems. Yet none of these models can explain the observed behavior. How does a magnetosphere powered by the rotation of a neutron star, containing more energy than humanity will produce in 1 billion years, simply turn off and on like a switch? What mechanism could simultaneously halt all radio emission while leaving the star's fundamental properties unchanged? How does the precise timing resume without any accumulated error after months of silence? Why do some neutron stars exhibit this behavior while others maintain constant emission for decades? What does the perfect preservation of timing during null states tell us about the relationship between neutron star rotation and radio emission? If magnetospheres can completely reorganize themselves, what other stellar processes might we be misunderstanding? As we've seen across these 10 stellar enigmas, the universe's most extreme objects continue to challenge our understanding in ways that suggest fundamental gaps in our knowledge of physics itself. 10 dead stars, 10 different impossibilities, 10 signals from objects that should be silent, predictable, understood. From the first pulsar's clockwork precision to the magnetar's apocalyptic bursts, from planets that survived stellar death to binary series systems that spiral inward with mathematical perfection. Each discovery has forced us to expand our models, revise our equations, acknowledge that the universe operates on scales and principles we are only beginning to glimpse. The pattern is unmistakable. Every time we think we understand stellar death, the cosmos presents us with another exception. Every time we build a framework that explains the data, another signal arrives that doesn't fit. These aren't minor inconsistencies. These are fundamental challenges to how we think matter, energy, gravity, and time behave at the extremes. The Vela pulsar's glitches suggest forces inside neutron stars we cannot model. The magnetar SGR 1806-20 generated energies that dwarf entire solar systems. The double pulsar system loses orbital energy at exactly the rate Einstein predicted, but exists in a configuration his equation said was nearly impossible to achieve. We are watching the universe perform at levels our physics can describe but not explain. Perhaps this is the true message these dead stars are transmitting. Not that our science is wrong, but that it is profoundly incomplete. We have built models that work within the narrow band of conditions where life exists, temperatures that don't instantly vaporize matter, pressures that don't collapse space-time, energies that don't rewrite the fundamental forces. But the universe operates primarily in the extremes, in magnetic fields trillions of times stronger than Earth's, in gravitational wells where space-time curves back on itself, in the final moments when matter achieves densities that turn atoms into pure information. These dead stars exist in the universe as it truly is, not as we need it to be to understand it. They are sending signals from the deep structure of reality itself, and we are only now learning to listen.